गुरुर्ब्रह्मा गुरुर्विष्णु गुरुदेवो महेश्वरः गुरु साक्षात् परब्रह्मा तस्मै श्री गुरवे नमः.
Hello, physics innovators, and welcome back. Last time, we were sketching ray diagrams, getting a feel for how these mirrors work. Well, today, we're swapping our pencils for calculators. We're diving into the essential toolkit, the new Cartesian sign convention, and the mirror formula that lets us pinpoint exactly where an image forms, how big it is, and whether it's right side up or totally flipped. Right, that's the big question, isn't it? How do we go from a pretty good guess to a perfect prediction? To do that, we need a system, a rule book that everyone in physics agrees on so that no matter who does the math, they get the exact same correct answer. Every single time. And that universal rulebook is called the new Cartesian sign convention. Honestly, just think of it as the rules of the road for light rays and mirrors. Getting this down is the absolute foundation for everything that follows. So what's this Cartesian thing all about? It just means we're going to treat our mirror setup like a simple graph from math class, with an x and a y-axis. It's a brilliant move because it turns a tricky physics problem into a much more straightforward coordinate game. Here's rule number 1, and it's the big one. The pole of the mirror, that dead center of its surface, is our origin. It's our 0, 0. Every single measurement we take starts right there. No exceptions. Okay, so we're treating the main axis of the mirror like our x-axis. And here's the convention. We always put the object on the left side of the mirror. Since anything left of the origin on a graph is negative, the object's distance, which we call u, is always going to be a negative number. Simple as that. And it follows, right, that anything to the right of the pole is positive. Now this is super important. When we calculate where the image forms, its distance v, and the answer comes out positive, that tells us instantly the image is formed behind the mirror, and an image behind a mirror has to be a virtual one. Now let's think about the y-axis, the up and down measurements. Any height measured upwards from that central axis is positive. This is going to apply to our object since we usually place it standing up, and to any images that are also formed upright or erect. And you guessed it, any height measured downwards is negative. This is the dead giveaway for a real inverted image. If you see a negative height, you know the image is hanging upside down in front of the mirror. And that's it. 4 simple rules that run the whole show. So now that we have the rules of the road, let's bring out the master tool that uses them. This is the one elegant equation that ties everything together for spherical mirrors. This formula connects our 3 key players, all measured from the pole, remember? We've got u for the object's distance, v for the image's distance, and f for the mirror's focal length. And there it is. The relationship is just so beautifully simple. 1 over the image distance plus 1 over the object distance always equals 1 over the focal length. That's the whole magic right there. The best part about this? This one little formula just works. It doesn't matter if you have a concave mirror or a convex mirror. It doesn't matter where you put the object. As long as you follow our sign convention rules, this formula will never let you down. That's its power. Okay, so finding the image distance v is awesome, but it's really only half the story, right? What does the image actually look like? Is it huge? Is it tiny? Flipped upside down? For that, we need another tool, magnification. Magnification, which we write as a lowercase m, is basically the decoder ring for our image. It's a simple ratio that tells us everything we need to know about the image's size and whether it's upright or inverted, all in one little number. And we've got 2 different ways to find it, which is super flexible. If you happen to know the actual heights, you can just divide the image height by the object height. But way more often you'll have the distances, so you'll use that second, really powerful formula. Negative v divided by u. Now this is where it gets really cool. The sign of m, just whether it's positive or negative, tells you the fundamental nature of the image. A positive m always means you've got a virtual and erect image. A negative m always means it's real and inverted. It's the perfect diagnostic tool.
All right, enough theory. Let's get our hands dirty and actually put this all into practice. We're going to take our complete toolkit, the sign rules, the mirror formula, and magnification, and solve a real problem to see how it all clicks.
Okay, here's the setup. We've got a convex mirror. First, the radius of curvature is 3 meters. Now, let's think. A convex mirror bulges outwards, so its center of curvature is behind the mirror, to the right of the pole. And our rule says anything to the right is positive, so r is plus 3. The focal length is always half the radius, so f is also positive, plus 1.5 meters. And finally, the object is 5 meters out in front on the left, so u is, you guessed it, negative 5. Now we just plug and chug. First, we rearrange the mirror formula a bit to solve for our unknown v. Then, as you see in step 2, we carefully plug in our numbers, making sure to get the signs right. 1 over positive 1.5 minus 1 over negative 5. A little algebra later, and boom! Step 3 gives us our image distance. V is positive 1.15 meters. Awesome! Now for magnification. We grab our distance formula, minus v over u, plug in our values, and step 6 gives us the final answer. And there's our number, positive 0.23. But a number is just a number until we interpret it, right? So what is this actually telling us about the image we see in the mirror? Let's break it down. First, the positive sign screams at us. The image is virtual and erect. It's behind the mirror and standing upright. Second, the value 0.23 is way less than 1. That means the image is diminished. It's much smaller than the object. And that is exactly what our ray diagrams told us to expect from a convex mirror. The math proves it. And that's really the big takeaway. Once you master the sign convention and the mirror formula, you're not just guessing anymore. You can precisely predict what light is going to do. These tools are the true foundation of geometric optics. Thanks so much for joining me on this deep dive. Now that you've got these power tools, go out there and bring the fascinating world of physics into sharp focus. Keep calculating.